Thank you so much. I can't believe I'm seeing real people in a real room at an event. It's fantastic, not seen that for a while. Thanks for the intro. So I'm going to elaborate a little bit there on who my organisation is just before we get into this. Some people have heard of us, but many haven't. So we're actually called the Bluetooth Special Interest Group. And as you heard, there we're actually a standards organisation. So we don't make things, we don't manufacture Bluetooth components or software stacks or anything like that. The primary kind of output from our work is a collection of engineering specifications that define the stack and its protocols and procedures and all that kind of thing, and some test plans. And it's actually implementers who are largely manufacturers who make Bluetooth components and systems and products and so on, and they all follow the same specs. And of course, the idea is that a product from manufacturer A will work with a product from manufacturer B as a consequence of that standardization. So we're all about interoperability through standardization. That's what we do. Now, as for myself, I guess I stand, or perhaps more accurately sit before you today with not a little trepidation, because I've never worked with audio in my professional career at all. And there you all are out there. Specialists and perhaps experts in your field and so on. And what do I know about audio? Oh dear. Perhaps a slight saving grace, those that's in my personal life. Audio in the form of music and music production has been part of my life for a really long time. And just to make clear exactly what I mean by a really long time, and to perhaps start off with a bit of a laugh, here's me in 1981. My age in that year is shown, so those of you who are wide awake can do some maths and figure out how incredibly ancient I am now. But more importantly, if you don't mind, there's my Roland SH09, my first synth, an analog synth that I still own. There's an amp there that I built from a kit, soldering every component to the PCB myself. First time I'd ever used a soldering iron at the kitchen table with my mum and dad looking on. Looking a little concerned, to be honest. Was there a mix-up at the hospital when we took him home? Or worse, could it be that our son is, oh my word, a geek? And they weren't wrong. I didn't disappoint them, because here's me in my first band, the aptly named Syntax Error, playing our first gig to an enormous audience. I don't wish to boast here, but an audience of around 6 people. That's true. Yeah, we were big in Darwin and Blackburn. More critically, though, sitting there on a table, almost out of shot on the left-hand side, there is a portable black and white TV into which I had plugged this, which is my first ever computer. It's the Sinclair ZX81 with a massive 1K of RAM. So I was learning to code then, and I think I had it doing some incredible blocky graphics with the band name, which ran until someone trips over the cable and unplugs it, presumably driven to dance and controllable by our music, or they were looking to flee the room. I'm not quite sure which now. So coding, electronics, been doing that stuff for a long time. These days, I'm an avid user of Ableton Live, and I create music of a genre I call MON DM, and the DM is not dance music, that's music of no discernible merit, but I don't care because I have fun. But anyway, maybe we have something in common after all, and maybe I should get on with talking about Bluetooth instead of all this stuff. So let's do just that. So everyone knows about Bluetooth. We all kind of use it in various products. You've probably got Bluetooth headphones, for example, like I do. But the Bluetooth of today is very different to the Bluetooth of 21 years ago. And I tend to think of it now as a toolkit for communication and location-based services. There are actually 2 forms of Bluetooth technology. One is called Classic, and the other is Bluetooth Low Energy. So Classic's the original. So Bluetooth Classic is used for data transfer and for audio streaming. And in terms of topologies, everything involves point-to-point connections between 2 devices. So you'll be familiar, I'm sure, with streaming audio directly from something like your phone to your Bluetooth headphones. Now, Bluetooth Low Energy is newer, it's very power efficient, and it's a lot more versatile. It supports those same point-to-point communication topologies, but it also allows broadcasting of data from one device to an unlimited number of receiving devices, which is pretty important. Where location's concerned, though, you can use it for presence detection and also for proximity applications where you determine that you're close to some point or object of interest and estimate your distance from it. And you can also use it for direction finding using a couple of techniques called angle of arrival and angle of departure. And we're also working on a high accuracy distance measurement capability too, so you can determine the distance between two devices. And then in the world of networking, we've got something called Bluetooth Mesh, and that allows networks of tens of thousands of devices to be created in things like smart buildings. And last but not least, we have this, because Bluetooth Low Energy is the foundation of the new LE audio technology. And of course, that's the subject of my talk today. So Bluetooth Classic is where it began about 21 years ago, and audio applications were amongst the first to use Bluetooth, with profiles like the hands-free profile for use in cars and the A2DP profile, providing support for wireless music streaming. Now, Bluetooth Classic Audio uses the SBC codec, and it supports one-to-one audio streaming between a single source device and a single sync device. And using the art of understatement, it's been quite successful. But whilst Bluetooth Classic has served our needs pretty well over the years, things change, and there are a number of audio requirements and product ideas that Bluetooth Classic Audio is not a good fit for. So, for example, Classic Audio is all about those point-to-point topologies with one audio source connected to one audio sync. But what about streaming to multiple syncs? What about public audio, which any number of people can tune into? Low power consumption, low latency, these remain constant requirements, but there's also a demand for better quality and an improved listener experience in some particular use cases. And it was to meet these kinds of new demands and to enable new audio product innovations that LE Audio was created. So let's start by looking at some of the basic features of LE Audio and get to know some of the new terminology that applies. So unicast audio is one of two options, the other being broadcast. And it involves one or more distinct sets of audio content being sent over connections between pairs of devices in what are called connected isochronous streams. Great word, isochronous, word of the day. So isochronous communication is a capability of the Bluetooth core protocol stack, and it allows us to group together multiple streams whose content must be rendered at precisely the same time. Now, to appreciate the significance of this, consider Bluetooth Classic Audio and how that works. So a product like my Bluetooth noise cancelling headphones has a single Bluetooth stack in it. It's physically installed on one side of the headphones. Both left and right stereo data gets included in each individual packet by the audio source device. And when my headphones Bluetooth controller receives a packet, the left and right audio data it contains is decoded using the SBC codec and then rendered in each of the two speakers with a wire connecting the side which contains the Bluetooth receiver with the side of the headphones which does not. But as you can see in the example of my slide, what I've got here is a couple of earbuds, each of which is an independent device with its own Bluetooth stack. Now, data for left and right stereo is delivered over separate Bluetooth connections to each earbud, but not at the same time. But because the two streams are members of the same connected isochronous group, the left and right audio data is rendered at the same time, and the listener hears perfect stereo audio. So the other way of using LE Audio is to use broadcast isochronous streams. With each stream, a member of a broadcast isochronous group. So this is based on connectionless communication and makes use of something called Bluetooth periodic advertising. Now, once again, the use of isochronous channels means that audio data in streams that are part of the same group will be rendered at the same time. And as the slide indicates, you can have closed broadcast groups, which are effectively password protected, or completely open public broadcasts. Now, using broadcast streams is very scalable and ideal for sharing audio with large groups of people, all of whom can tune their devices into the same broadcast audio streams. So imagine walking into a bar and being able to watch the game on the bar's TV with audio streamed to your earbuds, whilst everyone else who's not interested in football or rugby or whatever, still able to actually have a conversation. Imagine being able to receive announcements about your train whilst you wait on the station platform, right in your earbuds along with your music. So these are scenarios that Bluetooth LE audio makes possible in public spaces. So streams, which I've mentioned many times now, are effectively distinct audio content. And as you just saw, they come in two flavors, either connected isochronous streams or broadcast isochronous streams, both of which are grouped for synchronized rendering. So the most typical use case of streams is for left and right stereo, but we imagine it will find other uses too. Streams have an associated context. Now, a stream's context tells us what use case the audio relates to or its purpose. And context values can be discovered and can then be used in filtering and selecting streams of interest. Now, some types of device are used in sets of more than one, and actions need to be coordinated across all members of the set. So you'll typically want to change the volume of both your left and right earbuds, for example, at the same time. Now, the concept of coordinated sets gives us that capability, with devices able to be members of sets and control exercised over the set as a whole. Sets are identified by something called a private set random identifier, and they're secured with a set identity resolving key, or SIRK. Concurrent access to the devices in a set is controlled through lock and rank concepts, which ensure that there are no race conditions or side effects possible when more than one device tries to take control of a set. Now, devices can publish their audio capabilities using a service known as the Published Audio Capabilities Service. So this includes the codec or codec supported, the set of supported sampling frequencies, things like that. Also, the devices supported spatial locations, such as front left and front right. They're indicated by packs as well. And contexts, again, indicate the type of use case the audio is intended to be used for. So these attributes can be used in identifying suitable audio devices during a kind of discovery process. Now, broadcast audio uses this thing called periodic advertising, and it interleaves packets containing audio stream parameter data, timing synchronization data, and the audio data itself. The audio stream parameters and periodic advertising synchronization data are broadcast less frequently than the audio data. So consequently, when trying to discover and set up a broadcast audio stream, scanning, perhaps from your phone, may need to be carried out for longer periods of time to receive the information required. And scanning is a relatively expensive operation in terms of energy consumption, in other words, battery life, especially for constrained devices. So LE Audio defines roles and procedures which allow constrained devices like earbuds and hearing aids, which of course also have a very limited user interface, to ask another device like a smartphone, a watch, or a remote control to find broadcast audio streams. And this is called scan delegation. The device delegated to is called the broadcast assistant. Now, once the stream has been selected by the user using their smartphone, it hands over details of the selected stream and its timing parameters over a connection using a procedure that's been around for quite a while in the core Bluetooth stack called PAST. That's the Periodic Advertising Sync Transfer Procedure. So the phone with its big battery does all the heavy lifting and provides the user with a proper user interface to interact with. LE Audio defines quality of service in terms of a number of parameters such as sample rate and maximum transport latency latencycycy, and a series of standard QoS parameters are defined. Now, between them, these predefined sets offer various sample rates and offer either an emphasis on high reliability or on low latency characteristics. Obviously, which QoS parameter set is chosen depends on the product and its priorities. But what about security? Well, unicast audio is encrypted provided devices have been paired. Now, with broadcast audio, obviously the potentially unlimited number of receiver devices can't all be paired with the broadcaster device. So instead, a shared broadcast code is used to generate a session key with which to encrypt or decrypt payloads. A broadcast code can either be shared manually, perhaps printing it on a ticket and requiring ticket holders to type it into their phones, or when devices have been paired, it can automatically be distributed over connections prior to setting up the broadcast. There's also a new security key type, which I mentioned earlier on, called the set identity resolution key, and this ensures that membership of a coordinated set can't be faked. So that was an introduction to some of the interesting features of LE Audio. Let's now take a closer look at some of the technicalities underpinning them. So the first, and I think, key thing to know is this. LE Audio has been designed as a generic framework for Bluetooth audio products. And as you'll shortly see, it's not just one specification, but a substantial collection of specifications, and each spec covers a particular topic. And you could do worse than to regard them as describing audio product modules within a generalized framework. And the aim was to design something for creating audio products of the types we know today, as well as hopefully those which have yet to be invented. Now, the Bluetooth Low Energy core stack looks like this in terms of layers, and I've highlighted those features which are important to LE Audio. So first of all, LC3 is the low complexity communications codec. This is a new and better codec for Bluetooth audio. Now, as you can see, LC3 can be implemented either in the host part of the stack or in the controller. And for your information, if you're not familiar with those terms, a controller is usually a system on a chip, and the host is typically something like an operating system, and the layers of the stack get distributed across those two kind of major architectural components of a Bluetooth system. Now, the link layer in the controller there is where you'll find some key mandatory features that LE Audio relies on. Isochronous channels are part of the link layer, and their support is mandatory, and the same is true of periodic advertising, which broadcast audio uses. The isochronous adaptation layer allows source and sync devices to use different frame intervals. It performs fragmentation and reassembly, and it reconstructs the original frame timing associated with received packets. Then we've got something called the Enhanced Attribute Protocol, and it allows parallel execution of various protocol operations, and that basically ensures there's no risk of blocking operations and then impacting the user experience. And then we have these things called sub-rated connections, which I rather like. And they make an appearance in the latest version of the Bluetooth Core spec, which is version 5.3. They're not essential for LE Audio, but they can improve the experience of using some audio products in some situations. For example, sometimes we want to maintain a persistent connection between devices, so we don't have to take time setting up the connection when we want to transmit some audio. For example, a hearing aid user would want to hear their smartphone ringing instantly, and having a connection in place between the hearing aid and the smartphone all the time would help with this. But a persistent connection uses power. So there's a connection in radio communications of the duty cycle, and a low duty cycle connection uses hardly any power, but data transfer rates are very slow. Whereas a high duty cycle connection will use more power, but provide a higher data transfer rate. So obviously you want to conserve power, excuse me, when your connection is essentially on standby. So you start with a low duty cycle, but when there's some audio data to transmit, you want the duty cycle to be cranked up nice and high. But the problem is that changing duty cycle itself can be time consuming. So unless you use sub-rated connections, because we can have both our cake and eat it here with a low duty cycle and low power consumption when the connection has no work to do, and a high duty cycle and fast data rate when it does, and with next to no time taken to switch between the two modes. So sub-rated connections are not essential for LE Audio, but they're definitely useful. And there are various new profiles and services which we'll take a look at shortly. So the LC3 codec was developed by Fraunhofer and Ericsson. They describe it as a modern codec, possibly a successor to MP3 and AAC, or so I'm told, by people I know in the industry who know more about this than me. LC3 offers better quality audio for less bandwidth. So basically you get similar listening quality for about half the bandwidth, and this in turn means less radio airtime is required, which means you get some power savings too. Latency is low, approximately 25 milliseconds end to end. Excuse me, little cough there, let's have some water. So yeah, latency is low, about 25 milliseconds end to end, and there's a healthy variety of sample rates and bit depth supported for all sorts of different audio applications. And don't forget, it's not just about music. And LC3 licensing is covered automatically by the Bluetooth SIG license that all products must be granted, so there's nothing special anyone needs to worry about there. So isochronous channels are mentioned a few times, or at least the word isochronous. So what exactly are isochronous channels and how do they work? Well, they're a means of communicating what we call time-bound data to multiple devices in such a way that the data is processed at the same time by all receiving devices. So audio is a good example of something that involves time-bound data. And if you consider this, it's not possible for one Bluetooth device to transmit a packet containing, say, only left stereo data to one earbud, and another packet containing only right stereo data to the other earbud at the same time. Each earbud is an independent Bluetooth device, and only one packet can be sent by one Bluetooth radio at a time. So with isochronous communication, we create distinct streams to contain each distinct set of data, like left and right, and we group them. And then we transmit data, we transmit a packet over one stream at a time, with rendering delay parameters that result in the different streams data being processed at the same time by receiving devices. And in this way, processing, or in our case, rendering of data is performed in sync by all of the receiving devices. And as you've heard, we can create connected isochronous streams or broadcast isochronous streams, leveraging the connection-oriented communication capabilities of Bluetooth Low Energy on the one hand, and its ability to broadcast on the other. Now, there are various technical differences between these two approaches, but one thing they have in common is a fundamental strategy involving a reducing delay parameter associated with each stream in the group, which controls how long the receiving devices have to wait before rendering the data they've received. So what you can see on my slide is a depiction of 3 connected isochronous streams, each of which is a member of the same connected isochronous group. And precisely timed events in the controller determine which stream is to be serviced and when, in a kind of time-sharing scheme. Now, each stream has a different sync delay parameter associated with it, and as you can see, its value is shorter or longer depending on when the associated stream is to be serviced. So the first stream has the longest delay parameter, the second has a shorter delay time, and the third has the shortest of all. And receiving devices then wait for the delay time associated with their streams, and then they render the data. Now, I'm going to walk you through the main components of LE audio now, but to understand the architecture of the system, you need to appreciate the types of specification and their relationship. Understand the specifications and you understand the system is the theory. So there are 3 main types of specification. The Bluetooth protocol stack itself spans all layers of the OSI reference model, from the physical layer where analog properties of radio waves are used to encode digital bits, all the way to the application layer at the top. And the Bluetooth core specification defines the stack, its layers, protocols, and procedures. In other words, the core spec, all 3,500 glorious pages of it, defines Bluetooth. Profiles, on the other hand, are specifications that define how Bluetooth should be used in a particular product type or use case. So by adopting a particular profile, applicable products all communicate in the same way, and so they're interoperable. Services define state data that profiles use. So they reflect some aspect of the device and sets of operations you can carry out on that data in accordance with the rules of an associated profile. So there you have it. The core spec is the single defining spec for how Bluetooth works. Profiles define how products use Bluetooth, and services act as containers for state data and define how the operations that they support. Simples. So the LE audio specifications, we've got quite a few of them. On screen, you can see a summary. All except those depicted in grey have been released in full, or as we say, they've been adopted. That's the term we use. There's still a little work to do on some of the specifications, but they should be out pretty soon, and manufacturers are working through those that have been adopted already. So you can see that I've kind of grouped the specifications. Basically, we have the Bluetooth core specification, the LC3 codec specification, those specifications that apply to more than one product type sitting within the generic audio framework group, and then some use case profiles which we expect to apply to specific product types only. So working from the bottom of my slide, here's what we've got. So the core specification, obviously, with isochronous channels and the isochronous adaptation layer and the other key features that I mentioned already. Then we have the LC3 codec, for which there's a specification you can download now. Then the generic audio framework, that includes a collection of different profiles and services. We've got BAP, the basic audio profile, and it covers the procedures for establishing audio streams of both types. Then PACS, that's the published audio capability service, and it contains data items which describe the device's audio capabilities, such as which sample rates it supports, whether it can act as a source or a sink or both, what audio locations it supports, what contexts, and so on. And other devices can discover those properties when setting up unicast audio streams. It's about what a device is able to do and what it's currently available to do. Then we've got ASCS, that's the audio stream control service, and that allows an audio stream endpoint of a unicast stream to be configured and controlled. An audio stream endpoint in ASC has a state machine with states like idle, codec configured, and streaming. And ASCS supports operations that allow a unicast audio initiator to change between these states. And then we have bass, which I'm told is not pronounced bass, but I refuse to comply. It has to be pronounced bass, given this is audio. This is the broadcast audio scan service, and this is where we define the scan delegation and broadcast assistance system, which helps with the discovery of broadcast audio streams. It can also sometimes be used to wirelessly distribute the broadcast code, which is used to create the session encryption key for encrypted broadcast streams. Then we've got MCP and MCS, that's the media control profile and service, and they allow the remote control of media players. I think they make possible everything you'd expect. They use the concept of tracks and a media state machine to provide control of the audio. So the state machine allows a device using the media control profile to transition a media source through playing, paused, stopped, and seeking states like fast forward. And the user can also search for tracks, modify play order, and adjust the playback speed and things like that. Voice drying up a bit here. Then we've got CCP, that's the call control profile, and it defines, you probably guessed it already, procedures for wirelessly controlling phone calls. So this includes obvious things like making or answering a call, but also lets you do things like discover the name of the service provider, which could be a mobile network operator, the bearer technology in use like 3G, 4G, Wi-Fi, and so on, and the signal strength. And this makes it easy for client devices to provide a good user experience. TBS is the telephone bearer service, and it's used with CCP, and it gives access to telephone call control status for bearers on devices that can make and receive phone calls. Then we've got CSIP and CSIS. It's a profile and service concerned with coordinated set identification. So they define how the coordinated set thing I mentioned earlier works. And as you recall, the concept of coordinated set allows multiple devices to be treated as if they were a single device for some streaming and control use cases. Then NI, CP, and CS define microphone control procedures, things like muting and unmuting, either individual or groups of microphones. And then over on the right, we've got VCP, VCS, VOCS, and AICS. They're concerned respectively with volume control, volume offset or balance control, and audio input control. And AICS provides control for any input stream, by the way, not just Bluetooth audio inputs. And it allows things like multiple input streams to be mixed as well. Then above that, we've got CAP and CAS. They are the common audio profile and service. So as you can imagine, there are all sorts of common issues across the various aspects of unicast and broadcast audio streams, and CAP is where these common issues get dealt with. And the profile acts a bit like the glue for various use cases that span other profiles. And it also defines something called the commander role, which allows for the distributed remote control of audio devices. And up at the top, coming in the future, we've got use case profiles and services for telephony and media audio, hearing access, and the public broadcast profile. So TMAP, the telephony and media profile, that kind of pulls together combinations of lower level profiles to allow the establishment of configuration settings for various conversational, streaming and broadcast audio, telephony and media products. And this includes things like headsets, car kits, TVs, smartphones and personal computers. And hearing access, which might sound like a curious name, this includes hearing aids, but it's not limited to just those types of device. It covers hearing aids and all sorts of complementary products, things like doorbells even, which can generate Bluetooth immediate alert notifications, which hearing aids can respond to. In fact, hearing access refers to the fact that there's a whole ecosystem of hearing-related products, and these standardized profiles and services will make them interoperable. And finally, the public broadcast TV profile that defines program metadata to aid stream discovery and selection in public unencrypted TV. Note that the public broadcast profile is anomalous in having no accompanying service. That's a consequence of the nature of broadcasts where there is no connection for any kind of client-server interaction, and services really define the server end of these relationships. So for those, that great big list of specifications, they kind of fall within a number of functional groups, covering stream control, content control, transition and coordination control, and rendering and capture control. And hopefully this slide acts as a useful summary of all that detail. So let me briefly walk you through a couple of scenarios now so you can see how the various aspects of LE audio that I've mentioned might come into play. To start here with a unicast audio scenario where I want to use my earbuds with my phone, pretty common scenario. So here my phone is an audio source, and in terms of the common audio profile and the roles it defines, it's called an initiator, whilst my earbuds are audio sinks and they're called acceptors. So the phone advertises so it can be discovered, and it includes the identifying UUID of the audio stream control service in its advertising packets. So it's clear to other devices that might be scanning that it's offering unicast audio. Once discovered and selected by the user, connections are established and contexts, audio capabilities and quality of service requirements are determined through a conversation. This involves the published audio capabilities service or PACs, which I mentioned earlier on. Then configuration of key audio parameters takes place over the connections, and then connected isochronous streams are established and streaming starts. So that was unicast audio. Here instead is a broadcast audio scenario. So imagine you're in a hotel room. You're aware that your TV offers an LE audio service, and you want to listen using your earbuds because it's late at night and you don't want to disturb people in adjoining rooms, and you're a good person. The TV is using broadcast audio, by the way. So on being switched on, your earbuds, acting as a scan delegator, immediately try to attract the attention of some other device which can assume the role of broadcast assistant, and to which scanning for suitable broadcast audio devices can be delegated. And they do this using a technique called solicitation. So the smartphone, which you pull up an app on, it assumes the role of broadcast assistant, and it starts scanning for advertising packets that contain these solicitation requests. It applies some filtering so that only packets from devices it's been previously paired with are processed. And on identifying a suitable device, the phone connects to the scan delegator, which in this case is our set of earbuds. And then the phone, acting as a broadcast assistant, starts to scan for and discovers candidate broadcast streams, including the TV in the hotel room. The user selects the TV on the UI, and on request, it enters the broadcast code that they were issued with when they checked into the hotel. Then the phone, which has now collected periodic advertising parameters advertised by the TV, it now passes these details over its connection to the earbuds using the periodic advertising sync transfer procedure, which again I mentioned earlier on. So the earbuds now have everything they need to know about the stream that they need to set up. So they establish left and right broadcast streams with the TV and decrypt them using a session key derived from the broadcast code that the user entered on their phone and which was transferred using the PAST procedure. So that's LE Audio, or at least a short introduction to the technology. It is a big subject. But what else is current status? So where are we on this now? Well, as I said, there are a few specifications still to be completed and adopted at version 1.0, but it is looking pretty good. As you can see, companies have already announced the availability of Bluetooth LE Audio chips, and LC3 implementations, source code, and test tools are available now. There are open source stacks out there like Zephyr, if you've heard of that. They're implementing and have already released some of the key components like isochronous channel support. So that's it from me. Thank you so much for listening, whether you're in the room at the event or at home somewhere listening online. It's been great to talk to you guys today. I hope you found that at least an interesting taste of things to come in the world of Bluetooth and audio. Looks like we've got time for some questions now, but feel free to follow up if you think of something later on Twitter. My handle's there on screen, and I'll try and get an answer back to you. Thank you once again.
Great, thank you very much, Martin. So we can give Martin a hand here in the room.
Thank you. Cheers.
And yeah, it looks like we've got time for a few questions. So I will just take one of the ones that we got online first. So from Ichiro here, we've got, do you know any audio profiles for musical instruments which have one stereo input and one stereo output with BLE audio? Because there are only speaker config and headset config in Bluetooth Classic audio. I have to use USB audio to get audio stereo in and out in smartphones.
Right, yeah. Any permutation of source and sync is possible. It's incredibly modular and incredibly configurable. I don't think we have a profile as such for musical instruments with the specific requirement that musical instruments might have accommodated, but certainly the sort of general aspects of that question involving roles and permutations of role, anything is possible. This, I didn't mention it, this collection of specifications has been in progress for, kind of in development for, I'm just thinking about this now, I think it's about 6 years or something. It's been a really long path, and in the beginning it was really only envisaged that it would be for hearing aids. That's actually where the original kind of push for a new audio technology came from. And by the way, if you're ever interested, I mean, if you're generally interested in audio stuff, have a little read about hearing aids one day, because they are phenomenally complex pieces of amazing engineering, often with multiple microphones built in and digital signal processing going on. And of course, they're extremely power constrained. So battery life is extremely precious and, to be protected at all costs. So that was new to me as well. I found it very interesting reading about hearing aids and going, wow, I'm incredibly impressed with how those things work. So sorry, long answer to your short question. So nothing specific for musical instruments, but those permutations of source and sync, yeah, not a problem at all.
Great, and we've got a question from Florian here, which might be a quick one to answer. Can you recommend some affordable Bluetooth LE evaluation kits or boards?
For audio specifically, no. I need to go looking for that myself. I haven't gone looking for that yet. Not even sure if there are any out there. There may well be. But for general Bluetooth LE audio, there are loads of things out there. It depends what you call affordable. Right, I'll let you into one of my trade secrets now. Some of what I just did was live, me kind of just randomly making stuff up now, talking naturally to you, but I also have a kind of teleprompter type device in front of me right now. It's actually a smartphone application that I wrote, and I'm controlling it, the scrolling with this thing, which is a BBC microbit. And I think these things cost about £12. So this is a microcontroller device that you can program. So they're really, really cheap. You can program them using GUI tools that were created for 10-year-old kids to learn to code. So really, really simple stuff. Or you can use open source frameworks like Zephyr and program in C. So I kind of use quite a lot of those. I've got a box full of them, kind of looking around here. I won't go behind me. I've got tons of stuff. I use things called Nordic Thingies quite a lot as well. They're pretty good. Raspberry Pis, of course. I mean, Raspberry Pis are full-on Linux computers. I mean, these are the powerful end of the kind of Bluetooth LE device world. And I think a Raspberry Pi version 4 is about £25 maybe. I've got a Pi 400 as well around here somewhere. They're about £80, and they've got quad-core processors. They're really powerful machines. And then all of the main kind of Bluetooth stack manufacturers tend to have developer boards. So people like Nordic Semiconductor, Silicon Labs, you name it, Qualcomm, all those big names, go to their websites and you'll find something that suits your needs there. In terms of software frameworks, I'm a big fan of Zephyr. Zephyr's great because you're not tied to a single chipset or kind of manufacturer. It's fairly kind of platform agnostic. I think they support well over 200 different board types. So you can write your code in Zephyr using their framework, and you build for a particular build target, which is for the device type that you happen to have. And that includes BBC Microbit and the Nordic Thingy that I mentioned earlier on. So I tend to program all those things using Zephyr. So there you go. Yeah, that was a relatively easy question for me. Go for it.
Have we got any questions from the room in person? Oh, got one from Jay there at the back. Just bring you the microphone.
Yeah, I was wondering if you could comment on the possibility of multi-channel audio with this. I know with A2DP, the assumption of stereo is kind of baked in. Is it possible to go beyond that? Are there bandwidth limitations?
I'm glad you asked that question, because this is one I can actually answer. And I say that because I'm still voraciously consuming all the specs, and I'm still learning myself here. But yeah, channels are accommodated. Multi-channel is absolutely accommodated. It's a core part of the design. And within packets, you can include the data for one or more channels in each individual packet. So more detail, of course, on the spec there. So it was recognized that A2DP had that limitation, but it's not a limitation for LE audio at all. You asked another question kind of lurking inside the question there, which was about bandwidth limitations. And yeah, of course, there are limitations. So it's tempting, I guess, to look at the essentially the headline sample rates and things, audio parameters supported by LE audio, which ranges from, I'm going to get this wrong now, I'm going to say 48.1. I think that's the highest sample rate. And at the other end, I think it's 4 kilohertz, for different applications. But because of the sort of serial nature of the communication that has to happen between different devices in a group, you can't transmit different data to multiple devices at the same time with a single radio. You have to communicate to one device, then the next one, then the next one. And of course, you have time constraints. That's where the limitations start to come in. So with a very high sample rate, you've got far more data to transmit, and therefore you're going to eat into some of the available time. So there's always going to be a potential trade-off between the audio quality that you want or you believe you need for a particular use case, and things like the number of connected devices supported. Broadcast audio doesn't have quite the same constraints because you are communicating with an infinite number of devices that just have to be in range because we're not connected. We don't have that same concern, but multiple streams bring with them the same sort of set of considerations. You've got a time sharing system going on here. You've got finite time, so there's that potential trade-off between bandwidth and audio quality. But for the use cases that this has been designed for, I think we're quite confident it's going to work very, very well. Let me just caveat that statement because I don't want you to think that no one's tested this yet. We're having interoperability testing going on already. I'm pretty sure if you go looking on YouTube, maybe even actually our own website, bluetooth.com, you will find demonstrations of implementations already. So quietly confident that it's going to do the job. But let's let you guys decide whether that's true or not.
I think we had one more question in the room here.
You mentioned testing there. Are you aware of, able to recommend any sort of software testing platforms, frameworks, particularly for automated tests, particularly on Windows for testing Bluetooth audio?
Crikey, no, not at all, actually. And especially with that Windows requirement thrown in, I'm not sure that there's anything specifically for audio. Actually, sorry, my brain has just slipped into gear. This happens occasionally. So I'll give you a better answer here. It's not quite an answer to your question, but it still might be useful. Depends what you mean. So there's source code for LC3 you can download, and that comes with a testing tool. So you download the code and you build it and so on. My guess is you can integrate that kind of encode, decode testing capability within an automated test framework. You could certainly do that. Bluetooth itself, we provide a tool called PTS, that's the Profile Testing Suite. And product manufacturers actually have to use that as part of a process we call qualification. I think other standards bodies might call it certification, but we use the term qualification. That involves you taking your product through a whole series of test scenarios.